Hi class, in this next lecture, class number 2, we were going to talk about load analysis. As I told you previously, we have external loads. From external loads, we're interested in finding internal loads. How do we get to that? But before we do that, one step back, the concepts that you need to know from previous classes. You know your strengths of materials, so I recommend that you do some refresher from your strengths of material textbook. Here we're just going to give a review and expand upon what you already learned. And you also have to know how to find the centroid of a section because we're going to resolve all the loads about the centroid, and that's your responsibility to know. As we move on, so class number 2, and most of the material you can find it under my tab in D2L under topic number 1, load analysis. Here are the MATLAB files we will be using in the class. Here are my class notes, the homework, and the online video, which you already know because you're here. Okay, so as our discussion now, one of the things that you have to keep in mind, we're going to limit all our discussion to one-dimension analysis only. That's the scope of this course. So you have some sort of boundary condition, as I told you last time, some kind of restraint, and another type of restraint on this side. And let's suppose we have the case of a beam and you only has point loads. This could be a loading condition. You can have a loading condition where you got a distributed load, and or maybe the distributed load is applied only over a certain region only, and you don't have distributed load anywhere else. But in most of the cases, practicality is that we have a combination of both. How do we analyze this when we have a combination? First of all, if we assume that we have small deflection, let me change the point to this. And we also have small rotations. And my analysis can be considered fully elastic. Under those two conditions, under these conditions, I can use the principle of superposition that can solve this problem alone. I can solve this problem alone, and then the addition of this will give me the solution of this, right? And probably this you already learned in your previous classes. So the other thing that you have a lot is different type of boundary conditions. How do we manage these? Well, here what you know is in a problem like this, you will have a reaction in X, you'll have a reaction in Y, right? It's called a hinge or a pinned boundary condition. Here, you only have, I'm sorry, I mixed these. This is reaction in X, reaction in Y. If I use the coordinate system, this is X and this is Y. Here, I only have a reaction in Y. It's free to move horizontally. Here, glider is a very interesting case. Here, you are free to move up and down, and is restricted in Rx, and you also have a moment. So it's like the fixed case or clamp. The only difference is that we are relaxing in one of the directions. Okay, here you got, you have your moment in Z, sorry, your moment in Z, and it's fixed here in Z as well. Free, well, you don't have really any loads here at the tip because it's free. The next thing that you have to, that typically you know that your beams, in the analysis of beams, you have determinate beams and indeterminate beams. The determinate beams is if you have at least 3 unknowns. If you have 3 unknowns, they are called determinate beams. As for an example, you have 1, 2 unknowns. I have one unknown here. I go with 2 plus 1 is 3. 2 plus 1 is 3. I got 3 here plus 0 is 3. So this is statically determinate B. Statically indeterminate is anything that is 4 and beyond. And why is statically indeterminate? Because we only have 3 equations. We can use, remember, any summation in x, summation in y, summation in z. We can have a summation of moments in x, summation of moments in y, summation of moments in z. And I can only use, if I'm working in 2 dimensions, I can only use the any 2 of these. Okay? Those are the moments I can use. If I'm working only in 2 dimensions, I can use only 3 equations. I cannot use 4. So for this particular example, and how do we know this? So this is a very simple analysis. If it's statically determinate, do your section cuts and find your internal loads. Otherwise, if it's statically determinate, then you got 2 options. You can use compatibility equations to determine the redundant equation, or use energy methods to determine the redundancy. In anyhow, what basically you're doing is you're converting a statically indeterminate problem to a determinate one. Just remember one thing. We as engineers, we play smart. We don't like to complicate our life. I have a solution to something, and I want to know if my new thing somehow I can fit it into the something I have. So in order to do that, we do a bunch of tricks. That's what we are doing here. I got a statically indeterminate problem. I have the solution to statically indeterminate one. Is there a way I can take this one and I can convert it to this one? Yes, we can. That's the whole trick in this type of problems, is to convert a statically indeterminate problem to a statically determinate one. Okay? So there are many sign conventions that we can use. For the sake of this particular course with me, I am going to focus on the stress sign convention. This is the stress sign convention. You can have many other conventions. So if you see your mechanics of material textbook, you may have used a different sign convention. So this sign convention basically says that if I take, this is my beam, and if I take a small, infinitesimally small element, by infinitesimally small, I mean that this is basically 0. You don't have this element, it's a point. So I am basically, what we are doing is, I'm taking this small point, I'm expanding it, so it looks like a rectangular, it looks like a square, or it looks like a big element, but really it's a point. I'm expanding on that point. That's what we really are doing. So with that said, because this is an elastic material, my loads cannot be the same. There has to be some differential of that load, and the same thing, there has to be some differential of my moment. This is because it's elastic. Okay, this is the consequence of being elastic material. If it was rigid, then the loads have to be identical. I want you to think about a case in which I got this. This is acting as rigid. So all my loads applied here, they are completely transformed there. But it will make sense if this is elastic. Now this is, think about springs. So it makes sense that if I apply a load here, what is experienced on this side will not be identical, because the spring absorbs energy, and because it absorbs energy, it's going to absorb some of that load, or it's going to release some of the load, depending on if you're in a tension or you're in compression. Okay, so that's basically what we are trying to do here. And the sign convention says that when I am rotating counterclockwise on this side, it's a smiley face. Um, and one thing that I have realized throughout the years is that many times they just tell you how to use the area moment, and they use many other, just use tables, but you really need to understand where the equations come from. So in order to do that, what I want to do is I want to give you a quick derivation where these equations that we are going to be using, where do they come from? Okay, so give me a sec. So I care for this equation and where this comes from. It's very simple. If I take a summation in y, okay, taking y positive here, that's equal to 0. And I say minus vy on this side. And on this side, I have plus vy plus dvy. And then my total load here acting in the middle will be plus py times d of x, right? So this is equal to 0. And you can see my y's cancel out, and I end up with dy is equal to minus py d of x. Okay, so if I divide by d of x on both sides, I get this equation. So that means that if I know my shear, I can find my distributed load if it was not a point moment. Otherwise, this will be 0. If I have this variation is, well, I take the integral on both sides. And if I take the integral on both sides, I get vy minus the integral py dx, and I'm going to have a constant of integration. That constant integration, I call it v sub 0. That is the constant of what happens at the beginning, and this is what's happening at the point where I'm taking my moment, this is basically representing what happens here in this next section. Okay, don't get scared by the integration. That's very easy. And what does that really do? Okay, so if I was going to do the same thing for the moment is very easy as well. And the moment says the following. If I take now a summation of moment about z equal to 0, I'm taking this positive. And I'm taking a moment about this point. So this cancels out. I don't have to deal with it. That would give me positive moment. This is negative, so it's minus mz. Let's take care of the moments first. Mz z plus dmz, okay? And then this will be plus this right here, vy, and the distance is dx. Again, remember, dx is basically a point. This is just re-exaggerating this. And then if you know, you have to find the midsection, that this will be py dx times half of that distance. That will give you negative because it's going in this direction, minus py dx divided by 2 is equal to 0. So since this is almost as goes to 0, one of the things that you end up here is dmzz plus vy dx minus py dx dy is equal to 0. Okay, so in this particular equation, since we are assuming this is dx, we are assuming this is very, very, very small, the influence of this is not considered because it's already included here. So you basically end up with this variation of the expression minus vy dx. That's where you got a minus, and this is how these two are related. If I integrate on both sides, then I would get the same equation as previously explained. Now, usually, typically, life is not that easy because you really have a three-dimensional state of structure where you may have distributed moments, you may have a distributed load, you might have lateral uh, lateral uh, distribution, normal distribution, and transfer distribution with their own moments, and it may have some point loads. So how do you even deal with that? Well, in that particular case, your equations actually come from something more general, and this is what they're going to be looking like. You're more than welcome to pause the video and take notes of these equations. I am not going to derive this, a simple derivation about each one of those axes. Um, in general, how I'm going to solve these problems, uh, the solution to these problems is very easy. It's basically a systematic process. You have the external loads, move all the external loads to the axis of interest, and then you remove all the supports, find the reaction loads, find the load where you're interested, uh, determine your axial shear and shear forces, and from there you determine your moments. So this basically concludes load analysis lecture, and all I have done here is just give you the theory. In the next follow-up lecture, I will give you the examples.